In most situations, the purpose of using a transmission line is to connect a signal source to some sort of load that we have, and this load in electromagnetics is very often some sort of communications equipment, an antenna or an amplifier or something like that. And in these situations, for efficiency purposes and to protect equipment, it's ideal, or we would desire, that all the voltage and current that is sourced by the generator makes it into the load. What we're saying is that maximum power transfer to the load occurs when all the circuit is matched, when ZG equals Z0 and ZL. But often we don't have control over the impedance of the load. That's often a parameter of the load that we can't control, and we can't just always make custom cables. It's very common to find a 50 ohm cable or a 75 ohm cable, but finding cables of other impedances, they're very rare. And so the situation arises where we need to connect a load to a cable, and the load and the characteristic impedance of the cable are not matched in impedance. And under those situations, what happens is this reflection coefficient occurs. And we have a formula for reflection coefficient. It's ZL minus Z0 over ZL plus Z0. And what it tells us is how much of the incident voltage and current waveform gets reflected back towards the source. So it's also telling us how much power makes it through. Our task in building a matching network is that we want to put some sort of passive network in front of the load, such that the input impedance of that passive network in series with the load is equal to the characteristic impedance of the transmission line. And what this does is it causes the reflection coefficient to go to 0. It eliminates that voltage and current reflection at this impedance boundary. If we make this matching network exist of nothing but inductors, capacitors, and T-lines, then all the power that makes it into the matching network must be delivered to the load. And this is because we know from reactive circuit theory that inductors and capacitors, because they're reactive, they don't consume real power, right? There's no P in watts consumed in inductors or capacitors. And for lossless T-lines, the same situation exists. The definition of a lossless T-line is that no power can be consumed. So if this matching network is only made, if we limit our choices to these three elements, then we can construct a matching network such that we eliminate reflection coefficient between the impedance boundary of the cable and the load, and we make sure all of that power, real power, gets delivered to the load. The overall technique that we're going to use is that we'll utilize the Smith chart to determine a reactive element that can be placed in series with the load that's going to change that input impedance to equal the characteristic impedance. Additionally, the Smith chart is going to tell us how far away from the load that element needs to be located. So there are two critical things that the Smith chart tells us: what reactive element, whether it's an inductor or capacitor, that needs to be placed in series, and then also the distance from that reactive element to the load. So that's what we'll be calculating for these series matching networks. While we could use physical capacitors and physical inductors in series with the load, this approach isn't actually ever really used in application. And the reason is twofold. The first is that the approach requires cutting a transmission line and soldering in a capacitor or an inductor in series, and that will obviously compromise the cable that we're using. The second is that at high frequency, physical components become less and less ideal as the parasitic effects begin to dominate their behavior. However, as we've seen in previous lectures, shorted transmission lines and open transmission lines, we can make them appear as purely reactive elements, and we can very precisely control their reactance by adjusting their length, especially at high frequencies. And this property of open circuit T-lines and short-circuited T-lines makes them ideal for replacing these lumped elements in our matching network. So instead of using capacitors and inductors, we'll use open circuit and short circuit transmission lines. Most often instead of placing those in series, we'll place them in parallel with the load and located at some distance from the load. And this is called shunt stub matching because the network is shunted across the load, and we use these stubs, which are T-lines that are either open-circuited or short-circuited. So that kind of is a big, grand overview of what the purpose and implementation of these matching networks that we'll be designing for the rest of the day is.